Let's initiate the design of our library catalog system by applying object-oriented analysis. Our goal is to take a conceptual idea and transition from a real-world scenario to a modern program. To begin our analysis, we look at the requirements and start identifying nouns within those requirements. These nouns typically represent the objects that will make up our system. The primary object we identify is the book. A book is defined by a set of specific attributes. These are characteristics like the title, subject, ISBN, and the Dewey Decimal System number. The ISBN acts as a unique ID for the book itself, while the DDS number tells us exactly where the book is physically located on a library shelf. Another core object is the catalog, which acts as a manager functioning to organize and house the entire collection. Now let's look at the relationship between a book and an author. Here we apply the concept of association. This means the two objects are related, but it is neither ownership nor inheritance. A book is obviously not an author, so it's not inheritance. And while a book has an author, the author exists independently of the book. Also, because a book can have multiple authors or an author can write multiple books, our design needs to support a list of authors for each book. During this process, we also have some discarded objects that we evaluate but decide not to include in our initial model. For instance, the shelf is redundant because the DDS number already covers the location logic. Similarly, the user object is excluded to keep our design purely focused on the catalog search rather than tracking user subscriptions. Putting this all together, we can create our initial UML class diagram. The catalog class is here at the top, containing a public method labeled as search. A line connects the catalog down to the book class, showing their relationship. Inside the book class, we see all those attributes we identified earlier. Finally, we have the connected author class with its name attribute. This gives us our basic structure. But what happens when we expand our requirements? Modern libraries don't just hold books. They need to include new media types like DVDs, magazines, and CDs. While these don't use ISBN or DDS numbers, they share common traits like a title, subject, and a unique product code. To handle these variations efficiently, we introduce the inheritance concept. This allows us to create a general class and specialized versions, moving from a parent, superclass to child subclasses. Even though books use DDS, CDs use author last names, and DVDs use genre to organize every item needs a way to be found, which we'll handle with a common method. Let's look at our updated UML with inheritance. The catalog class is now linked to this centralized library item class. The numbers 1 and asterisk indicate a one-to-many relationship. The library item acts as the parent, holding all the shared attributes and a universal locate method. Below the parent class, notice this arrow pointing upwards from our 4 specific subclasses. This means they inherit from library item. Because of this inheritance, the magazine class only needs to list its unique volume and issue attributes because it automatically receives the title and UPC from the parent. The core takeaway is that object-oriented analysis helps us map real-world entities into structured classes using concepts like association and inheritance to build a flexible and efficient system. To understand how these objects actually communicate when performing a specific task, we'll dive into sequence diagrams next. To understand how our library objects communicate during a specific task, we use what's called a sequence diagram. Unlike class diagrams, which just show the static, fixed relationships between things, sequence diagrams are dynamic. They show the actual flow of messages back and forth over time. Let's do a walkthrough of a search for a specific item, like something with the keyword bunnies. First, look at these vertical dashed lines coming down from the top. These are called lifelines. They represent the existence of an object as a time passes from top to bottom. At the very top, we have our participants, the user, the catalog system, and two specific instances of library items, a bunnies book and a bunnies DVD. The process kicks off when the user sends a search message to the catalog. Notice how right when that happens, a thin vertical rectangle appears on the catalog's lifeline. These are called activation boxes. They show exactly when an object is actively awake and performing a task. When there is just a dashed line without a box, the object is idle, just waiting. So, the catalog is active and needs to find the items. It sends a locate message to the bunnies book. The book wakes up, processes the request, and returns its specific physical location, which is a DDS number, via a dashed return arrow. But the catalog isn't done. It next sends that exact same locate message over to the bunnies DVD. Now, a DVD doesn't have a Dewey Decimal System number. Instead, the DVD returns its genre and title to tell the system where it is in the media section. Finally, the catalog compiles this information and sends the combined results back to the user. This entire sequence is a perfect illustration of a powerful concept called polymorphism. As you can see down here, the catalog calls the exact same locate method on both a book and a DVD, but it receives entirely different types of return data based on what specific type of object it is talking to. Ultimately, polymorphism allows our system to ask different objects to perform the same action, trusting each object to handle the details in its own unique way. Now that we see how items handle their own data dynamically, we'll need to figure out how to efficiently track the various people who create these items, like authors, actors, and directors. Now that we understand how objects communicate, our design must address what we call the contributor problem. Let's look at the initial problem. Historically, in our system, books had authors, but DVDs have actors and directors, and CDs have artists or narrators. Using completely separate attributes for each specific role across different classes is highly inefficient. A more flexible approach is to recognize that all these roles, authors, actors, narrators, are essentially just types of contributors. By moving this relationship up to a parent library item class, we can allow any item to have contributors. Let's look at solution 1, which uses a many-to-many association. In this first attempt, a new general class called contributor is connected to our library items. This establishes a many-to-many relationship. This means one item, like a movie, can have many contributors, and one contributor, like a famous author, can be linked to many different items in the library. However, this design has a major flaw. It does not specify the actual role of the contributor. We might know a specific person is associated with a DVD, but we do not know if they were the director or an actor. To fix this role issue, while trying to maintain what we call polymorphic elegance, we might try solution 2, abstracting the interface. We could add a getContributor method to the main class, allowing subclasses to manage their specific contributor types internally. But look at the diagram for this approach. This quickly becomes a spaghetti design. Notice the multiple lines crossing back and forth between the contributor class and the various subclasses. While this technically functions, it is extremely fragile. Any change to the contributor class might require updates to
every single subclass. It completely lacks maintainability. So, we arrive at our final design, solution 3, which utilizes refactoring and composition. Refactoring is simply the process of improving internal structure without changing external behavior. Instead of relying on complex inheritance, we use composition alongside a supporting class to clearly identify those roles. Notice how a new class is introduced here. Contributor with type. This class acts as a bridge. As you can see in the diagram, it is actually composed of a standard contributor plus a specific type attribute such as director or author. This allows us to connect a library item to this new bridge class. We can now add any number of people in any number of roles to any item without ever needing to touch the core class code. If we need a new role tomorrow, like translator, we simply change the data in the type attribute rather than creating an entirely new class. It's incredibly flexible. This progression highlights a critical lesson in software engineering. Inheritance is not always the best solution. For instance, down here, we see a rejected design. It uses inheritance to create many empty subclasses like actor, translator, author, just to identify different types of contributors. Creating empty subclasses just for labels is unnecessary and clutters your system. In summary, achieving the final design balance is about using the right tool for the job. You should use inheritance for major structural categories like different types of library items where their core behaviors actually differ. However, as the scale illustrates, you should lean heavily on composition and helper classes for roles where the only real difference is a descriptive label. This balance creates a highly cohesive system that is both easy to extend and maintain in the